get started today. The whole point of Lewis structures was really to get down into the kind of nitty-gritty of the basic bonding patterns that you would expect for the more common elements. So the most common that you're really going to be dealing with are actually those last, was that 4? Carbon, nitrogen, oxygen, and your halogens. Those are going to be the more important ones. So if you know that all of those atoms are supposed to be neutral, there's a certain amount of bonds that those atoms will always have. Right? So if carbon is neutral, it will have 4 bonds. This does not say anything about bonds to the same atom, right? But it has 4 bonds. For instance, if we took at the compound C2H2, could end up with this form or with this structure. It's actually our only option. Each of those carbons still has 4 bonds. Right? It just so happens that 3 of those bonds are to the same atom. Okay? So when we look at an atom, we want to make sure that we always have the proper amount of bonds. So if we'd added an extra carbon, so sometimes this shows up, put an extra carbon here and put a double bond. You should now panic because that center carbon has 5 bonds, and it cannot have 5 bonds. Right? Lots of different reasons why. The most important one for our sake is going to be it's exceeded its octet. We cannot exceed the octet for carbon, nitrogen, or oxygen, or really for the halogens in OChem. Okay? The other thing that we could then watch for is what happens if our atom becomes charged. So you will find that carbon, nitrogen, oxygen, and your halogens will potentially be charged in your structures. Okay? Because they now have charge, they're going to have a slightly different association of bonds around them, okay, depending on what they're looking at. You need to be familiar with those bonding patterns, because if you've got those bonding patterns down, it's not a question of how many valence electrons are in my structure, how many atoms do I have, how many octets, what's the formal charge. It's there. You know that if you have a positive on a carbon, that carbon's only going to have 3 bonds. It cannot have more than that. It cannot have less than that. Okay? So having these kind of ideas at the back of your head can really, really help out. Okay? So spend some time to draw out some Lewis structures. If you feel like you're getting tired of drawing out a whole bunch of Lewis structures, that's fine. Go through and just memorize the bonding patterns. Okay? Questions? Once we've got the bonding patterns, other things to take into consideration. Okay. Does the shape of the molecule change the potential interactions? Yeah, it's going to have a significant effect on how that atom can interact with other things. So we have to be familiar not with just the standard bonding patterns in Lewis structures, but then what happens when we move these things into 3-dimensional shapes? How does that change reactions? Okay, so we have to have an understanding of shape, which this textbook has it slightly differently organized than my slides. It's a little bit confusing here. What we're going to do is take a pause from our shape and come back into drawing organic molecules. So if you were given the structure, or sorry, the formula, C5H12, what's the Lewis structure? Spend a little bit of time here, see if you can't come up with a structure for this. And unless you're cheating and looking ahead at the slides, I'm going to tell you you're wrong, just so you know. Or we allow somebody else to have gone through and looked at a whole bunch of different Lewis structures to notice some patterns. Because remember, carbon can have 4, or has to have 4 bonds. So if we fully saturate everything, what we end up with for a formula for a saturated compound is CXH (2x plus 2). So if a structure is saturated, which is officially Y, it's not X, right? If a structure is saturated, it matches this formula. So if we take a look at our formula that was given, what was X? 5. Okay. If we plug this now into our saturated formula, what is 2 times 5? 10 plus 2? 12. So it is a fully saturated compound. This means in the drawing, you cannot have a multiple bond and you cannot have a ring. Okay, so that can be helpful. Your unsaturated formulas can vary off of that. So it's not as fun to look at those, but we could try and draw something up. CXH2X. Okay, we can potentially see some variation, but for the most part, it's 2 times X. Actually, that's a lie. So I can already think of exceptions to that. XY. Okay. So if you see a formula that matches the saturated, no double bonds, or triple bonds, or rings. Right? If it does not match that formula, then you are looking for rings and double bonds showing up in this. So since we're looking at the saturated formula, we could go through and draw out a bunch of possible Lewis structures. Right? I noticed that almost everybody picked where you put them all in a straight line. Good call. Right? So let's address some issues with putting it in a straight line. Right? From our organic simplifications, how can we simplify our structures? Oh my gosh. Did I got it all? Can't believe I am doing this. So we've got this straight line option, right? It's a lot of work, drawing all those atoms. What can we do to simplify it? Okay, we can define every point to be a carbon. Okay, so we could go through and do something like this. Then what could we do? Did I get all my hydrogens? One more side. All right, that simplified it down a little bit. I can imply the hydrogens. So let's go through and imply the hydrogens now. Try and be careful with my erasing. Whoops, got a little. How many carbons are now in my structure? If we do it as a straight line, that gets kind of difficult to pick out our carbon atoms, right? So what can we go through and do? We can zigzag it. Okay, we can kink it so that we can pick it up and see what's going on with it. All right? That formula doesn't really give us a lot of options, or it gives us way too many options. We can draw a lot of different possible compounds that come out of it. Right? But if we switched it up and gave you this formula, would our previous answer have worked? Would that have been correct? No, because when we look at this formula, it's now changing how we focus on our molecule. It's saying we have a CH3. Okay? I'm just going to abbreviate it as a CH3 here. But I'm saying there's 2 of them. Okay, well that wasn't all that difference. We had 2 CH3s before. But that parentheses is now saying that those 2 CH3s are connected to a single carbon. Right. We didn't have that in the previous case. We had a big long line. Okay. What is that carbon then connected to?
Another carbon and a hydrogen.
A hydrogen, which is drawn right to the right of it. Okay. But then it's still missing a bond. Okay. So we can then imply the other carbons trail after it. So our initial drawing of a formula is pretty useless because we can come up with a variety of different compounds to match that formula. Okay, so what we want to do is shift out of our standard formulas and we'll start to see structural formulas. The structural formula starts to bring in some of that connectivity. How are you connecting each of those individual groups to each other so that we can get to a better answer? Why might that be important? Well, are the physical properties of this compound versus our straight chain carbon different? They are significantly different. Right? That difference now makes a drastic change in how the molecule reacts with other things, and we run into problems. Okay? So we want to make sure that when we're talking about a particular compound, we are very specific. We're referring to a single compound and not the class of compounds that match a formula. So we start to disappear away from formulas and move into structures. And this is where we can get our Lewis structures, which we got drawn up there, and I'm now about to delete it. Okay, but then we can start to introduce some other information to this. Okay, we talked about having a flat line, okay, being a bit tedious to see, okay, a bit difficult. So we can move to a line angle. And we could go through and show in all of our atoms. And even that gets a bit tedious to go through and show. But what we're trying to do is at least add a little angle to it so that if I did go through and simplify, I can see each of the carbon atoms. So my carbon atoms become just points. So we could look at a line angle abbreviated in this case, where we've implied carbons and we've implied all of the hydrogens. Why can we imply the hydrogens? Well, what type of bond is there between a carbon and a hydrogen? Single bond. Keep going. We haven't talked about sigma yet, but that's technically single bond. What type?
Non-polar.
Non-polar covalent. Does a non-polar covalent bond want to interact with anything? Nope, because it's neutral. So that bond, as far as chemistry goes, is relatively useless. So we can ignore its presence, okay, or we can imply its presence, rather. And we end up with this structure. So that when we look at that center carbon, we can now start to draw some conclusions or information about it. One of those conclusions being, if we look at how many bonds are around that, how many bonds are shown? 3. But if it has 3 bonds, it needs to be charged. We can't ever imply charge. So if there's no charge shown, what does that mean? There's another hydrogen filling in that octet. Okay, so our simplifications can help us draw our structures quicker. The issue with that is that hides information. Depending on what you're trying to do, that may be hiding very useful information, or it could be completely useless, right, depending on what you're looking at. The other aspect we can bring in, which is what we're going to talk about probably for most today, would be this valence shell electron pair repulsion theory, which ultimately gives us shape. Okay? Lewis structure gives us no information about shape. And we drew out our line angle, and we put in the angled bonds. Why did we make them angled? So we could see the carbons easier. It's actually based on the shape, not so that we can see the carbons easier. Okay? The shape that's associated with a carbon with 4 bonds is tetrahedral, with bond angles being 109.5. So when we draw out our line angles, we're trying to match that 109.5 degree bond angle whenever we draw out our structures. Is that strictly necessary to do? No, but it can help us see the molecule in its actual shape, its real shape. What we're trying to do is mimic the 3D world as best as we can, and that is not an easy task to go through and do. So when we look at the VSEPR model, what we want to try and do is introduce that shape into this. Our VSEPR model for this molecule will probably come out looking like this. Are there other ways that we could draw that 3-dimensional shape? Yeah. Is one more correct than another? Nope. Okay, and that's a very kind of unfortunate thing. We can draw out these structures a million different ways. All of them are equivalent. The only thing that's going to say why one structure is better than another is depending on the person drawing it, okay, or trying to use that structure. If you can interpret and understand how the structure is drawn, then that way is the best way to draw it for you. Okay. When we drew this up, you'll notice that we added a little bit more information. What was that extra information? I drew that bond a little bit different than I drew all the others. What is that supposed to represent?
It's actually coming out at us.
The bond is coming out at you. Okay? You guys all look awfully excited today, so I won't do the demonstration. But if something gets closer to you, what happens? It gets bigger. It's usually where I run at people and trip over things. Objects get bigger when they get closer to you. What happens when they move away from you? Smaller. So how can we show our smaller? Our notation is to use a dash. The atom that is dashed in this case would be that hydrogen. Do I have to show the hydrogen? No. But what I'm trying to do is, as best I can, reflect what's going on there. If I want to add that information in, there it is. Okay? Questions? So again, with our simplifications, we're really only concerned about roughly 10 elements. We'll deal with simplified shapes and hybridizations. We haven't talked about hybridization. That's in Chapter 3, but we'll deal with shapes today. And we'll look at simplified drawings. Every point is a carbon atom. The only way it becomes not a carbon is if you say it's something else, and we do that by using that symbol. Hydrogens are almost always implied to carbon, and they will be implied to carbon to satisfy carbon's octet. So if I draw out this compound, how many hydrogens are in it?
4. Or no, 12.
Yeah, 12.
Every point is a carbon atom. So if we layer in our carbons over the top of this, we will imply hydrogens to satisfy carbon's octet. Our center carbon has how many bonds?
4.
4, which means it has?
That's not that.
It has its octet, no hydrogens. The outer ones all have 3 hydrogens. So if all 4 carbons have 3 hydrogens, we have 12 hydrogens total. Kind of makes sense? Next rule in our simplification. We will never, ever, ever imply charge. Okay? Charge must always be specified. And one of the primary reasons, that, or our first example of it, can happen in this case. Okay? If we drew this structure out, actually let me erase all that. If we draw that structure out, that center carbon looks like it only has 3 bonds. Well, according to Rule 2, I can imply hydrogens, which means that carbon actually has 4 bonds. If I implied the charge on that carbon, which charge did I imply?
That would be a positive charge.
Because you guys memorized this already, right? Carbon with 3 bonds is positively charged. Carbon with 3 bonds is, can show up as negatively charged as well. Okay? We can't imply charge. It's really, really horrible to do. We'll lose hydrogens potentially, and we're going to not be able to determine reactivity, be it negative or positive. Okay? Where you guys might be saying is, well, when it was negatively charged, it had a lone pair. Except what happens when we move to Rule 4? Lone pairs are very often implied. Right? Even on carbon, though most typically they're implied on nitrogen, oxygen, and halogens. Why do we imply them? You start drawing out your Lewis structures where you had to draw all those dots in enough times, you get sick and tired of doing it, and you start to imply them. That becomes exceedingly dangerous when we move into the second half of the semester. Because what happens in the second half of the semester? We look at reactions. Well, to do a reaction, what has to move? Electrons. If I've now implied the location of all of my electrons, they're no longer drawn, which means if I look at a structure, I don't have electrons to move. Okay? So I'm going to try my best throughout this semester to never imply hydrogens. Okay? That said, I will do a horrible job of it because I don't like drawing all the stupid little dots. Okay? Electrons. I said hydrogens, didn't I? Electrons. The electrons is what I will try to never imply. Okay? Those will always try and be drawn on. Realize when you move through chemistry or organic chemistry, it will start to get implied for your electrons. Okay? Hydrogens, we're going to run into a similar issue. Okay? They're almost always implied, but there are a few reactions where we involve reacting a hydrogen that's bound to a carbon. Well, how do we know it's present? we'd have to go back and realize that we can add hydrogens up to carbon's octet, and even though it's not drawn, it may be implied and can allow all sorts of other reactions to occur. Okay, so you need to be super familiar with these simplifications and make sure that you're always including or not including them, but realize why you're doing it. Okay? Which can get dicey. After that, we can jump into VSEPR. Okay, so Lewis structure allows us to give us the bonds, but it doesn't give us anything about shape. Okay? And that's where Lewis really fails. Okay, the example that we could come up with would be if we looked at methane. Let's actually switch it up. Let's go to a better example. Let's look at dichloromethane. So we've got a carbon with 2 hydrogens and 2 chlorines. The reason why Lewis fails is that if I draw the Lewis shape for this, or Lewis structure for this, I can come up with this structure, right? Does everybody agree? Is there another structure I could have drawn?
You've drawn the chlorines opposite of each other.
Put the chlorines on opposite sides. So this was actually something I'd always wondered about on how we knew Lewis structures really failed to draw shapes. The assumption based on how we draw these is that what's the geometry of those atoms around that carbon? What's it look like? Is that what it looks like? It looks square planar.
Right.
Okay? So that if we move to a compound like dichloromethane, would we expect it to be polar or nonpolar? Depends on how I drew the structure, okay, which becomes a bit problematic. So we could go through and say, okay, we pick a sample of dichloromethane and we look at it, and we find out that it's polar. We take another sample of dichloromethane and we find out that it's still polar, and another sample, it's polar. All of them are polar. Well, if these are 2 valid possible options, at some point I should be able to pull a sample of dichloromethane that is nonpolar. Never able to do it. What does that mean about the square planar argument? It doesn't work. It's invalid. Right? Because one of our drawings should suggest that it's nonpolar, but it's always polar. That means there's something else going on with it. That's where we moved into the tetrahedral shape. And that's where we had to come up with some other kind of way to describe and predict shapes out of these things. Right? So the example I typically like to go with would be methane. And if we drew out our methane structure, we could look at this and say that our bond angles must all be equivalent. Why must they all be the same? So all hydrogens are all exactly the same, which means the bonds should all be exactly the same, which means the bond angle here being 90 degrees should be the same as the bond angle here. 90 degrees. So what's the problem with my structure? What's that bond angle?
180.
180. Is that the same? No, it's different. So we run into yet another issue on why this doesn't quite work. So that's where we can go through and say, okay, what do we know about what's happening within this structure? Now let's just pick the carbon as our center point, and we can put the hydrogen somewhere on the outside. What keeps those hydrogens around that carbon? Okay, for instance, we've got all our hydrogens around it currently right now, but if I went through and did this simple maneuver, how many hydrogens are bound to that carbon? Only 3. So what's keeping the hydrogen attached to the carbon? That magic little line. What is that magic little line? Electrons. Okay. So I've got electrons in each of those lines. What happens when electrons get near electrons? They repel. So each of these groups needs to repel away equally from each of the other groups, which then puts us into our tetrahedral shape, because we've got 4 equal things, and we can go through and try and draw it out with our VSEPR model. as a tetrahedron. This is one of the most notoriously difficult shapes to see, at least in organic chemistry, so we'll come up with a couple options for you to play around with. Number one, option number one, nice straightforward simple one. You bought a model kit. Use the model kit. It's the easiest way. Number two, carbon's my palm, hydrogen's my thumb, other hydrogen's my index finger. But that's only 2 hydrogens. And in fact, those would be the 2 hydrogens that are here. Right? Where are the other 2 hydrogens? One's coming at you. Where's the other one? Going away. There's a tetrahedron. Right? Nice and straightforward. So if you're now trying to figure out where different things are, you can now shift and rotate that. And so when we look at our drawing, we've picked a hydrogen and another hydrogen to be in the same plane. The other 2 are now going the other direction. They're trying to mimic the way we got it. It's like that, right? Right? That allows us to get some interpretation of those shapes. The other one that's more embarrassing, but it works. These are now my hydrogens. Where do the other 2 hydrogens need to be? Going towards you?
And behind.
They're going away from me. You now have another tetrahedron. All right? Being aware of these shapes and how they manipulate is going to be of critical importance after exam 1. That's when we start to look at this concept known as chirality, and it's really around tetrahedral atoms. So you have to be able to manipulate and see these structures in 3 dimensions. All right? So we can end up with a variety of shapes based on the numbers of electron groups around an individual atom. You'll notice that I'm saying electron groups. So we can get tetrahedral, trigonal, planar, and linear. Fantastic. All right, so we've got those set up. So if we looked at methane, which we already did, our CH4, and we looked at its Lewis structure, we'd say we have how many groups of electrons? 4. 4 distinct bonds. What if we looked at ammonia, NH4 plus? Careful. Still 4. Positive charge means there are not electrons there. All right, so we can associate that positive charge in there. What happens if we now move to ammonia versus ammonium? How many groups of electrons? Still 4. Okay. So the shape I would predict for this would be tetrahedral again. Okay. We run into yet another issue. Are all of the groups of electrons around ammonia the same as they are around methane or ammonium? No. There's one set of electrons that is different because it is not in a bond. Should that affect how the electron clouds disperse and push away from each other?
Yes.
Yeah, we've now changed that local arrangement. So we would expect a shape change. Let's, how much space do I have on the next page? I do. So let's try another one. We know our methane, but let's try this one. This is just to be obnoxious. How many groups of electrons? 4 around our carbon, right? And I already made the mistake of not implying electrons. Or sorry, implying electrons. So what shape? What shape would we expect for that compound if there's 4 groups of electrons? Tetrahedral. But to be tetrahedral, what do we have to say? They're all equal to each other. Are all those bonds equal to each other? No. Is the shape for this compound strictly tetrahedral? No. If we think back to what we were talking about in lab, we get a spectrum of interactions, a spectrum of bonds, a spectrum of forces. We get a spectrum of shapes as well. We try and classify them as best we can, but we are going to get variations outside of that. Right? And it's all based off of how we defined these shapes. We picked atoms with equal bonds on the outside. That got us our primary electron shapes. Then we realized that we have differences in electrons. So if we have bonding electrons versus non-bonding electrons, that's going to change our shape. Okay? And that's where we come up with these other shapes. Trigonal pyramidal and bent being our two secondary shapes that come out of this. And the difference there is that we're now looking at bonds versus non-bonds. We can further refine this and say, oh, if I put on a different atom, that's going to change the shape. So we could come up with a new sequence of shapes, which would be really exciting and fun, because we can now go through and look at all sorts of fun new shapes. Except it's really tedious and boring, so we don't do that. All right? What we have to acknowledge is that these are not strictly defined as the only shapes. We can get variations off of these depending on our geometries around it. We picked these shapes as our primary shapes because this applies to probably 95% of the cases. Okay? So you guys are now responsible for being able to acknowledge and see these different shapes and what that means as far as how those molecules interact with each other. Okay? So how can you go through and do that? I personally like this nice little shape summary, looking at our groups of electrons. So it's a pair of electrons. Actually, let me change that. It's a side of our center atom that has electrons. We'll talk about that side in just a second. We can have up to 4 groups of electrons. That gets us our electron pair geometry, or our shapes. We then differentiate between bonding and non-bonding. Once we have the bonding and non-bonding, that gets us to our molecular shape. And when we move to the molecular shape, the only things we're concerned about are not electrons, but molecules and ultimately the atoms that make them up. So we can't really call it atomic shape, okay? But that's really what we're looking at. It's the arrangement of the atoms around our center atom, which then generates different bond angles. Do the bond angles matter? Sort of. Okay? Depending on what you're trying to do around different atoms, we might want a wider bond angle. Because a wider bond angle means part of that center atom is now more exposed. If it's a narrower bond angle, part of that atom is now closed up and entrapped. Right? So we have to be familiar with how these shapes can potentially change on us. Questions?
Those angles eventually come into play when they're reacting with other.
Yes. Very limited circumstances, but yes. The angles will come into play, particularly when you're looking at substitution reactions. Okay. I said, how are we going to determine electron groups? So let's skip that for a moment, come back to this. Nobody's ever heard this, or at least I doubt you've heard of it. Where did Lewis structure originally come up with his model? Anybody know what he based everything off of? He had this octet rule, right? What shape has 8 points? Octahedron is true. There's another shape. Close. Remember, this is three-dimensional. We're looking at a box. Lewis's original paper on Lewis structures had everything drawn out with boxes. What was at each point? Your valence electrons. And when we tried to look at bonding between different atoms, we drew another box. And we said we could form a bond between these two faces because the electrons could sit in the vacancy at the other spot. Whew. So what are we trying to draw? We're trying to show bonding by drawing cubes for every single atom. It's a bit dicey, so what do we simplify to? You simplify a box down to a square. How many faces on a square? On a square. 1 face, 2 faces, 3 faces, 4 faces. That's where you check for your electron groups. So if we draw out the Lewis structure for methane, where are there electrons around our carbon? Well, is there an electron pair on this face? Is there one here? 4 faces. Cool. What happens if we switch this up to carbon dioxide? How many electron groups are now around our carbon? So everybody jumps to 4. Remember, where did Lewis structures come from? A cube that we simplified to a square. Are there electrons on the top face? Are there electrons on that face? Yep. Are there electrons on this face? Are there electrons on this face? How many groups of electrons? 2, which puts us at the linear shape. So we aren't counting bonds, we're counting groups of electrons. And this group concept gets very confusing, because when we look at a double bond, we might say, oh, that's 2 groups. But those electrons are actually a single group on a single face of our square. Okay? So where it becomes tricky is when you see those multiple bonds. Question? Okay. There isn't a whole lot else I can say about VSEPR models other than looking at those shapes and coming up with them. I would recommend that you try and build the models so you can get familiar with those 3-dimensional shapes, particularly tetrahedrons, so that when you rotate, spin, or flip them, you know what they look like. As a quick example, if I take this tetrahedron, let's put a bromine there. That's a Br. And I rotate about this axis. What does that look like? To 180 degrees. What does it look like?
The bromine
Come out, does, and then go back.
Oops, that was a CO. Okay. That simple manipulation makes a massive difference when you move through chemistry. So you need to be able to manipulate these and draw these at any individual orientation. Okay, so I would recommend pull out your model kits, play around with the tetrahedrons, and see how your structure changes. Take the model kit, toss it up in the air, or grab it, turn it on its end, look at what the structure looks like. Evaluate and draw that. Okay? Functionality. All things strive for neutrality. Okay? Everything does. This is why when you stick a fork in an electrical outlet, the electrons flow out of the wall and into the ground to neutralize that charge. We're trying to dissipate all of that energy. So when we're going through and looking at individual bonds and structures, what we're trying to do is neutralize that charge as best as possible. Okay? We don't need to worry about how we got to that excited state, okay, or that higher energy structure. What we're concerned about is now that we have it and we react with something else, what can happen afterwards. Okay? All of that comes back to electronegativity. So we want to know what our most electronegative is, and we want to know what our least is, and generally have some concept of how they are. Okay? So what we'll look at in organic chemistry is connecting different atoms to each other. When we connect, say, a hydrogen to a carbon, that has drastically different chemistry than a hydrogen connected to a nitrogen. Because the chemistry changes so wildly, what do we end up doing? We name it something else. Okay? We can't call a hydrogen bound to a carbon anymore because the carbon's there. Okay? So we go through and we come up with these different functional groups. And we can look at possibilities of our sigma and pi, which again we'll see in a little while. This being a single bond, and our pi being a multiple bond. In this case, really a double. That changes the functionality, so we change the name. You need to be familiar with all of those different names so that when you look at a structure and I say, where's the carbonyl, you can point to it. Or I can say, how does the carbonyl react? You can figure it out. Right? So that's where all the functional groups are ultimately coming from. We change the chemistry drastically enough by connecting those atoms to each other. Right? What happens if we combine several of them? Okay, so these I would call as our primary functional groups. Let's take a carbonyl, which is a carbon-oxygen double bond, and I connect it to an oxygen-hydrogen single bond. So the oxygen-hydrogen is hydroxy. The carbon-oxygen double bond is carbonyl. What do we have drawn here? Carboxylic acid. If we combine our simple functional groups with each other, get them close enough to each other, those chemistries can interact with each other. When they interact with each other, depending on that interaction, it may change the chemistry enough that we end up with a higher order functional group, like the carboxylic acid. Right? So in general, we try and keep them separated for first semester. As we move into second semester, you'll take 20 functional groups, you jam them all in the same structure, and you have to figure out how they all affect each other. Right? So you have to be aware of these manipulations. So, next part, reaction versus interaction. Before we can get a reaction, we have to get an interaction. We have to get things to interact with something else. All right, we saw a similar version of this in the lab, so let's kind of go through and process this. If I take sodium chloride, NaCl, and I want to look at an interaction. How does it interact with other molecules? Which interaction is favored? Top or bottom? Why is the top one the favored interaction? I don't quite accept that. Ionic means that we're generating charge, so we could specify with more information. How do we know the positive is on the sodium and the negative is on the chlorine? Chlorine is more electronegative than sodium, so it takes the bonding electrons away and it becomes negative. If we then apply that to the other atoms, we get more charges showing up. Now, which interaction is favored? The top, it becomes favored because I take a negative and I put it next to a positive, which means what happens to the charge? Neutralizes. Everything strives for neutrality. If I look at the bottom interaction, negative to negative, what do I get? We could look at a repulsion. Well, let's say there's no repulsion. You get more negative, okay? More charge. Higher state, bad situation. So we don't see the bottom interaction. We see this top one being favored. All right. What happens when we move to that or the next example down, CH? Which interaction is now favored, top or bottom? So we do the exact same argument that we had before. Okay. We're at a point now where there's nothing to help us predict. There is no charge differential here. If we look at the bond between carbon and hydrogen, that is a nonpolar covalent bond, which then means no charge is associated with either of those atoms all the way through it. Well, if it starts neutral, does it care what it reacts with, be it neutral or charged? No, because there's no balancing. It can't go anywhere from neutral. So both of those options are available to us. The question then becomes, well, is that a different interaction than we had before?
Yes.
Yeah, it is a different interaction. Well, if it's a different interaction, just like we did with functional groups, what do we have? We have to name it something else. All right, so what do we name each of these things? And this kind of comes back to however we want to name it. When it comes to our first example, it's most typically referred to as ionic, which is a horrible name because it's not a bond. What we're looking at in that dashed line is not a bond. But if we look at our definitions for what we have as bonds, we have covalent and ionic. So ionic shows up as both a bond and as an interaction or a force, even though they are drastically different things. All right? Sometimes you'll hear people refer to it as electrostatic. Okay, it's an attempt to become less confusing with reference to the force. When we look at the bottom case, what happens there? Should it be stronger or weaker than the sodium chloride? Should be weaker, because we're already looking at neutral interacting with neutral. So that shouldn't do anything. Right? So we would expect a super strong interaction for the top and a weak one down below. How weak is it? To a first approximation, there is no reason those two molecules should interact with each other. So as scientists, we approach it and say, well, if there's no reason for them to interact, the attractive force is exactly 0. Well, if it's 0, do I need to worry about it? No. Well, if I don't need to worry about it, should I name it? No. So we end up not having a name for that for the longest time until a scientist came along and said, actually, you're wrong. It does actually have an effect. We do have to approach this and look at the energy associated within that attraction. It just happens to be incredibly small. Because of that, we tend to remember the name for the guy that discovered this. That person's name was van der Waals. The other option you'll see is London dispersion. Okay, I have no idea why it's called London. I wish I could make something up on the spot, but I'm not going to. But the dispersion actually makes sense. What does it mean to disperse? Spread out. It's how something spreads out. Well, ultimately, what were we looking at in both these cases? We're looking at how electrons interact with each other. So in our lowest case, our lowest energy force, it's how the electron clouds around each of those molecules disperses. And well, should that dispersion matter? Well, if I take a nucleus, draw a little nucleus there, and now I draw an electron. Okay, what charge is the electron? What charge is the nucleus? A nucleus will be positive. If I'm now going to be this little purple star and I come in to this atom, what do I see? What do I see first? The electron. What charge is the electron? If I'm now that star coming in from the other side, what do I see? See the neutron first. Nucleus first, which was positive. So depending on how that electron disperses around the atom, I'm going to see slightly different charges. Okay? Why this is so drastically weak is that what's happening with that electron? It's constantly moving around. Okay? So what we're looking at is very random temporary dipoles showing up. These temporary charges, based on the dispersion of the electrons around the atom, are what are causing the attractive forces. Right? So if our star comes in as a negative, it comes up from the right-hand side, it temporarily sees a positive. So it goes, hey, we can neutralize, and they start to interact with each other. But then what does the electron do? Hop, skip, and a jump right next door. What happens? Now it repels the other molecule away, but on the other side, then what happens? That one can temporarily be attracted. So we get this kind of temporary attraction between these. All right? So when we're looking at our molecules, we have to be aware of how they're connected, the individual atoms. We have to be aware of their shapes. And then we also have to be aware of the differences in electronegativity, because the differences in electronegativity predict charges, and those charges are what's going to determine all sorts of physical properties that can pop out of this. Oh, wow. I had those already drawn on there. So that's where we end up with the difference between our intra and intermolecular forces. Intra being within the molecule, also known as the bonds. Our inter being outside the molecule, how different molecules interact with each other, and that we label as forces. Right? And we come up with these kind of classifications. It's a bit disingenuous to go through and just show them, oh, these are separate things. They aren't separate things. This is the interaction between any two atoms. If those two atoms interact very, very strongly, what ends up happening? They have a bond. But what if that interaction is relatively weak? It's a force. So depending on what we're trying to classify and what we're looking at, we're going to come into separate different categories. But they're all ultimately the interaction between any two atoms, period. All right? We talked about our definitions of our ionic, polar covalent, and our covalent. Those then translate into our forces. And if we had an ionic bond, that translates into an electrostatic force. Because our molecules are charged. The bonds are charged, which means the force between those bonds is also charged. So we have an electrostatic attraction. If we go through and looked at our covalent bond, where we had our carbon to hydrogen, that was all neutral, which meant that we don't get an electrostatic interaction. We got something relatively weak. The only way we get that weak interaction is that we generate London dispersion forces. So if we look at the bonds, we can now predict the forces. Once we know the forces, we can then look at reactivity, we can look at solubility, we can look at melting point, and look at a variety of different things. And all of that comes back to that initial classification within our bonds. Okay? The one extra thing that we'll tag in here that I think is extra information will be our rules for hydrogen bonding. First rule for hydrogen bonding. What is it?
Hydrogen donor and an acceptor. Hydrogen bond donor.
I'll actually classify that as the third rule, but I'll get back to yours in just a second. I heard a lot of people say hydrogen needs to be bound to nitrogen, oxygen, or fluorine. That physically must be present in your structure, and that's a bond. What type of bond? Polar covalent. It has to be a polar covalent bond. Why? Is there a difference between nitrogen, oxygen, fluorine, and hydrogen? Yeah, there's a massive difference in electronegativity. That gets us our polar covalent bond. All right. Rule 3, we have to have a hydrogen bond acceptor, which means we have a hydrogen, okay, and a hydrogen bound to nitrogen, oxygen, or fluorine. And then we also have to have our hydrogen bond, whoops, I did that wrong. We have our hydrogen bond donor, which means we have a hydrogen bound to nitrogen, oxygen, or fluorine. Our acceptor has to be able to accept the hydrogen. Well, what charge was the hydrogen? If the hydrogen's positive, and that's our donor, what should our acceptor be? Negative. Our acceptor has to be oxygen, nitrogen, or fluorine. All right, so if we have those two set, we're clear. The first rule that nearly everybody seems to skip over and miss, because the rest of them are kind of self-explanatory from that, you have to have a dipole-dipole. That means molecule A has to have a dipole, molecule B has to have a dipole. Well, if you have hydrogen bound to nitrogen, oxygen, or fluorine, there's your first dipole. Okay? So those could be your 3 classifications of hydrogen bonding. Questions? Did skip over a lot of that, but that's mainly because we talked about it in lab. And we're going to talk about it in lab again and again and again. So we got all the functional groups that come out of all of these interactions. Okay? As we move through the semester, we'll start to evaluate each of those charges and start to interpret how they can interact with other molecules. If we summarize all of our bonds and forces into one big colorful wheel that takes a little bit of time to interpret, but I've had students come back and insist on seeing it again. If we have a sky blue type of bond, what type of force mimics? Come across back to the sky blue color. Right? So if you have a it's a covalent bond, we have what type of force? London dispersion. If you have an ionic bond, you have what type of force? Ionic, or electrostatic. If you have a polar covalent bond, you have what type of force? Oh, way to not fall for the trap. You have dipole-dipole. Once you've determined you have dipole-dipole, what should you do? Now look for hydrogen bonding. Okay? It's a full-on spectrum all the way across, and it's not perfect. Okay? We've arbitrarily dropped those lines and said anything that's bluish is covalent bond, non-polar covalent. Anything that's greenish is polar covalent. Okay? Completely arbitrary. Okay? So these properties go through and give us melting points, boiling points, solubility. You can even look at vapor pressure if you really wanted to. And it'll also drop you into reactivity. Okay? That reference down at the bottom, I should have caught. That's to our old textbook. Don't worry about it. Okay? You're supposed to read everything in our textbook, so don't stress on that. So what can we do with this? Well, let's take a look at some examples. Phase changes. Took a look at those top 4 compounds. Which one would I predict to have the highest melting point? So what is a melting point? It's the change from solid to liquid. What keeps something a solid? Careful. The forces. It's the intermolecular forces between the molecules. When we phase change, we don't touch any of the bonds. Right? So if we're now told to rank those, or even to come up with just the highest melting point, what we need to do is think about the force that's holding those molecules together. Well, a highest melting point is going to have which type of force? Strongest or weakest? Which is the strongest force? Ionic or electrostatic. So now we look at our compounds and try and determine, do we have ionic or electrostatic forces? Well, it's a bit of a dicey subject because the forces are between molecules. We don't see a second molecule here. It's assumed. Okay? It's implied. So we can't look at the second molecule that it's interacting with. What do we need to do?
Look at the charge.
We need to look for what makes that type of force. So an ionic force comes from an ionic bond. All right, how do we know we have an ionic bond? Couple answers. Everybody's jumping to the answer because it's on the screen. What's the other answer? Metal and a non-metal. Sometimes you'll be given the metal, sometimes not, so you have to figure it out. Okay, we don't have the metal here, so what's our other definition for an ionic bond? We have to have a big enough difference in electronegativity to generate charge. So we look at these molecules. Is any one of them charged? Yep. Which one's charged? It's far right, which means we're looking at ionic interactions, which means we're looking at the highest melting point.
Is that the highest boiling point also?
Will also be our highest boiling point. Okay, well, that was really straightforward. That's just multiple choice, 1 out of 4. That's easy. Okay, how do we make it harder? Rank them. Right, so to go through and rank, what do we now have to do? Well, do any of the other compounds give us ionic? No. Okay. Well, to do any ranking problem, you need at least 2 things.
Also have it.
No, you need at least 2 things to rank. You need a first and a second, right? Okay. Right now, we're only looking at 1. So pick one other thing. All right, so we can pick this one. Do not pick all 4. Pick one other molecule. And now when you look at that compound, we want to look at its forces. We don't have a second molecule, so we can't look at its forces. So what do we do? Look at its bonds. What type of bonds do we have in this molecule?
Dipole.
Bonds.
Covalent.
Bonds. Polar covalent, because we have an oxygen. Polar covalent bond means we have what type of force? Dipole-dipole, which is weaker than our ionic. So if we're going to say our highest was 1, okay, we know this number has to be something lower than it, 2, 3, or 4. Okay? Might be helpful to write down what the force was. What force did we get out of that? Hydrogen bonding. So all we've done is now answer the first part. We've now ranked 2 things, but you got to rank all 4. So what do you do now? Pick another one.
Polar covalent.
I heard a first one, so we'll do the first one. What do we do with this? What are the bonds? Which gets us to London dispersion forces. Is that weaker or stronger? Weaker. Right, so we could now start to say that we're probably looking at that one as being a 2, and this next one is 3 or 4. Now what do? We add in one more, and look at what's left. We see polar covalent bonds, which means dipole-dipole forces. We can compare the dipole forces to our ionic. Oh, weaker. We can compare the dipole forces to our hydrogen bonding. Weaker. Okay, well, if it's weaker than 2, it must be 3 or 4. We now compare it to our first one, and stronger, we end up with 4. Whoops. No, I erased the right one. And 3. Okay? So it's a very tedious, slow process of manually checking your way through. Right? Because I don't want to do the next one in full glory detail. Which one of these 2 has the higher melting point? How I would go through and evaluate this is based on the structures that I see. Carbons and hydrogens, check. I can now ignore those parts of the molecule because they're the same in both. If I look at the other molecule, one's got an OH, the other one has an OH. Well, those are the same. Which is going to interact stronger? Nothing or something? Something, which means our higher melting point would be our something. Okay? Yes?
Why do you say that hydrogen bonding is stronger than
Hydrogen bonding is a stronger form of dipole-dipole because of a bigger difference in electronegativity than most dipole-dipoles. So that's typically why hydrogen bonding gets ranked higher. Here, it's not a question of hydrogen bonding being stronger because they both had hydrogen bonding. So they're both equally strong as hydrogen bonding. I can't see a difference between those.
No, I mean the sorry, the first one, the second, the one, the 1, 2.
Oh, up here? Why was this 2 and that 3?
Exactly.
Yeah.
Hydrogen bonding.
Hydrogen bonding is a stronger example of a dipole-dipole force. Yeah.
Just because of the
In general, yeah. You can push it all the way to electronegativities. Carbon versus oxygen is... Anybody know? Good. 1.2. The oxygen-hydrogen is 1.4 as a difference. So you get a larger difference, which means a more polar bond, which means a stronger intermolecular force back off of that wheel. Repercussions that come out of this, we can look at melting points and boiling points, which is what we just looked at. What resists the phase change? The resisting of the phase change is not our bonds, but the forces. And the forces are derived from our bonds. So we can look at a structure where we see bonds, and we can predict what happens with the forces. Okay? So if we're looking for species that have higher melting points or boiling points, we're looking at compounds that have more polar bonds, more ionic characteristics. Okay? The other one is we could look at solubility. Right? It's the ability of two substances to mix with each other. Right? For them to mix, they have to have similar forces, because in the pure state, they're already trying to neutralize their forces as much as possible. So if I take an ionic compound, actually I got it on the next slide, I think. We're looking at this like forces dissolve like forces. It's not quite on the next slide. It's on the next slide after this. So solvent terminology. So first things that we could look at would be what happens with our solvents. You'll come across 2 horrible, horrible words and should never ever be used to define any answer. Okay? Polar versus nonpolar. Okay? And that's because these terms are way too vague to do anything with. Okay? So we do run into this. For you to have a polar solvent, really what we're saying is that we have a solvent that has polar covalent, or really ionic bonds. To have a nonpolar solvent, we have nonpolar covalent bonds. Okay, which means our difference in electronegativity is really, really small, less than 0.05, same to same, or carbon to hydrogen. Okay, but we can have compounds be nonpolar that don't match these bond descriptions. So calling polar versus nonpolar is kind of meaningless until you go through and explain why they can be classified as polar or nonpolar. The next thing that can come out of this is a term that's a little bit more appropriate. You can get protic versus aprotic. What does protic sound like? Proton. Whoops. So we're looking at proton. What symbol does a proton have? Fair enough. I can't run with that definition. I really wanted to do H+, but that doesn't work because we haven't talked about it yet. So H+ is our standard application for proton. Right? So when do I get a positive hydrogen? When it doesn't have an electron, but if I'm looking at a solvent, I'm not going to be looking at just H+ floating around. It needs to be connected to something. So how does hydrogen get as close to being positive as possible? To having a bond to a very electronegative atom, nitrogen, oxygen, or fluorine. So protic really just means a hydrogen bonding solvent. What does aprotic mean? Not hydrogen bonding. Okay, does an aprotic solvent have to be nonpolar? Not necessarily. Because we could take a compound like this guy. Anybody recognize this compound? Nope. It's a ketone, it's acetone. Acetone is actually a very polar solvent, but it is aprotic. Why? We don't have a hydrogen bound to oxygen, nitrogen, or fluorine. Right, so it's just a definition term that comes out of this. We'll pick up here on Wednesday. We'll go through and look at solubility as a couple examples, which will be the end of Chapter 2. We'll move into Chapter 3, which I will tell you will be a bit of a beast because we're looking at hybridization theory. And I've noticed most people don't like hybridization theory.